Now let's continue with chapter 13, ring opening reactions of epoxides. This section is long enough, I think, that we can cover it separately from the last two sections. So, epoxides are very useful synthetic intermediates because of their significant ring strain. They're reactive towards both weak and strong nucleophiles. And examples you'll see are Grignards, hydride reagents, alcohols, and alkoxides. Strong nucleophiles react readily with epoxides. And so, for example, hydroxide will attack this. Remember, these two carbons are both going to bear a partial positive charge because oxygen is very electron withdrawing. It is high in electronegativity, second only to fluorine. And so here the ring opens. This is an SN2 process, and then this generates the alkoxide, which plucks a proton off of water. So this gives you the diol. You've already seen this synthesis a number of times, I think. The ring opening reactions of epoxides are thermodynamically favored. You can see that here the epoxide is an ether, of course, and it's high in energy because of the ring strain. So even though the cyclic ether and the acyclic ether go through transition states that have very similar heats of formation, the energy of activation for a cyclic ether, the epoxide, is much lower because you're starting with a much higher energy reactant than a typical acyclic ether. Epoxides can be opened, therefore, by many other strong nucleophiles, so alkoxides, cyanides, bisulfide, Grignards, lithium aluminum hydride. It is regioselective and also stereoselective. And so this means you're going to have an SN2 reaction, backside attack, and it will always go to the end opposite that of the hydroxyl, the alcohol functionality. So this position is less sterically hindered, and so you're going to have nucleophilic attack there. Under basic conditions or neutral conditions, you're going to have attack by the nucleophile at the less sterically hindered end. So that is a very simple and logical rule for you to remember. That should be no problem. The stereoselectivity, you'll get inversion of configuration observed at the carbon where the nucleophile attacks. Under acidic conditions, though, is a little bit more complicated. Acidic conditions, you can open the epoxide under acidic conditions with just a weak nucleophile. So here, the first step under acidic conditions, of course, is going to be protonated. And now oxygen normally withdraws electron density from both of those carbons. And when it's bearing a positive charge, it's going to withdraw electron density even more so. The oxygen is going to be even more electron withdrawing. And so here you're going to see the rules about which end of the epoxide does the nucleophile attack. They're going to change a little. They're going to be a little more complicated. It's not purely steric effects. So, water or an alcohol can be used as the nucleophile under acidic conditions. The epoxide is made much more reactive by protonating the oxygen. This is the method that antifreeze is made by industrially also. Just a little side note. So the acid catalyzed mechanism, you have protonation, then both of these carbons are partially positive, even more so than under neutral or basic conditions. And when this happens, you have attack by water at one of the carbons, and then you need simply to deprotonate to give you the product. So this is pretty simple. This is not going to create a problem. And so under acidic conditions, the nucleophile, if it has a choice, still occurs at the less substituted carbon, just like under neutral or basic conditions, unless you have a tertiary carbon. And if you have a tertiary carbon, that trumps everything under acidic conditions, not neutral or basic conditions. So only under acidic conditions, if you have a tertiary carbon, and it doesn't matter if the other end is primary or secondary, if you have a tertiary carbon, you will have attack there, okay, as shown here. So it's just in that one circumstance that you will have to remember. Under acidic conditions, where you have a tertiary carbon, you will have attack at that carbon. So what's happening is when you protonate the oxygen, both of the carbons are partially positive. But this carbon, since it is tertiary, is better able to bear a positive charge, a partial positive charge. And so it opens up a little bit, and this partial positive is a little bit greater than at the other end. And so in that case, you will have the nucleophile attack here. The other end could be primary or secondary, it doesn't matter. If you have a tertiary end, that is where you will have attack under acidic conditions. If you do not have a tertiary carbon at either end, then it's still dominated by steric effects, just like under basic or neutral conditions. So this is the one exception where you have to remember that it's dominated by electronic effects. It won't be dominated by electronic effects up here because the secondary carbon simply isn't stabilized enough. Here the tertiary carbon is stabilized enough under acidic conditions that attack there dominates. The ring opening reactions of epoxides under acidic conditions, inversion of configuration still is observed. So the point is that even though this is opened up, okay, there is still enough bonding between oxygen and carbon. You do not have free rotation about this carbon-carbon bond. There is still sufficient bonding there. The bonding is not lost. And so that means that you still have inversion of stereochemistry here. When the the alcohol comes in to do a backside attack, you will still get inversion of configuration there. So that tells us that that bond is not completely broken. Okay, so I hope that that has explained this. And in the next part, we will go on looking at thiols and sulfides.